There was a time when hearing a Silverado fire to life meant one thing: reliability, not flashy technology, not turbochargers, not hybrid systems, just the unmistakable rumble of a naturally aspirated American V8 that seemed capable of surviving anything. Construction crews trusted it, ranchers depended on it, fleet managers bought them by the thousands because they simply refused to die. At the center of that reputation sat one engine, the Chevrolet 6.0-liter Vortec. It powered work trucks, heavy-duty pickups, cargo vans, ambulances, school buses, police vehicles, motorhomes, and even military applications. Millions of miles were logged with these engines pulling impossible loads, idling for hours, and taking abuse that would destroy most modern power plants. But then, Chevrolet killed it. Most people assume they already know why. They blame emissions, they blame fuel economy, they blame government regulations. But what almost nobody realizes is that the real story is far more complicated. Because the 6.0 Vortec wasn't discontinued because it suddenly became a bad engine. In fact, it may have been too good, and what happened behind the scenes changed the future of every GM truck that followed. To understand why, you have to go back to the late 1990s. General Motors had a problem. Actually, they had several problems. Its legendary small-block V8 had evolved through decades of development, but the automotive world was changing rapidly. Competitors were producing stronger, lighter, and more efficient engines. Customers wanted more horsepower while expecting better fuel economy. New emissions standards loomed on the horizon, threatening engines designed decades earlier. Ford had completely redesigned its truck lineup around the new modular V8 platform. Dodge was preparing to resurrect the Hemi name. Import brands were capturing market share with modern overhead cam designs. Meanwhile, GM's venerable Gen the second small block was showing its age. It still worked, it still sold, but everyone knew its days were numbered. The engineering teams at GM faced enormous pressure. They needed something that could compete for the next 20 years, something versatile enough to power everything from sports cars to cargo vans, something efficient enough to meet future regulations, yet strong enough for commercial duty. GM needed something entirely new. The answer arrived in 1997. Engineers introduced the Gen the third small block family, internally known as the LS architecture. Although enthusiasts remember engines like the LS1 powering the Corvette, truck buyers received a completely different branch of the same family. These became the Vortec engines. Among them was the legendary 6.0-liter. Depending on the application, it carried engine codes including LQ4, LQ9, LY6, L96, and several others. Each version served a slightly different purpose, but all shared the same fundamental DNA. The block used deep skirt cast iron construction with 6-bolt main bearing caps. That design dramatically increased crankshaft rigidity compared to earlier generations. The casting process itself represented a significant advancement. Engineers utilized computer modeling to optimize metal thickness. Critical stress areas received additional reinforcement. Unnecessary weight disappeared. The result was an iron block that weighed less than previous designs while actually becoming stronger in key load-bearing zones. The bore measured exactly 4.00 inches. Stroke came in at 3.622 inches. Multiply those numbers across 8 cylinders and displacement reached 364 cubic inches, or 5,967 cubic centimeters, marketed simply as 6.0 liters. Compression ratios varied depending on the version. Early LQ4 engines ran roughly 9.41. Performance-oriented LQ9 versions increased compression to 10.11, boosting output without sacrificing durability. Horsepower ranged from around 300 in early work truck trim to 345 horsepower in the high-output LQ9. Torque stretched between 360 and 380 pound-feet depending on calibration. Those numbers don't seem extraordinary today, but in 1999, they were monsters, especially considering these engines were expected to tow trailers weighing over 12,000 pounds, day after day, year after year, without complaint. And that was only the beginning, because the engineers had built something incredibly over-engineered. The crankshaft spun inside an exceptionally rigid bottom end. Cross-bolted main caps prevented crank flex under heavy loads. Oiling passages ensured consistent lubrication even during long uphill grades while towing. The oil pump itself received significant attention. It was positioned to maintain prime even during steep inclines. Bypass valving prevented excessive pressure that could damage bearings. Pan design included baffling to prevent oil starvation during hard acceleration or cornering. These weren't racing features, they were commercial duty necessities. The camshaft remained in the block, operating 2 valves per cylinder through hydraulic roller lifters and pushrods. Simple, compact, remarkably durable. Some critics mocked the pushrod design as outdated. European manufacturers had moved to overhead cams decades earlier. Japanese brands built entire reputations around high-revving DOHC engines. Even some domestic competitors embraced more complex valve arrangements. GM engineers saw it differently. Fewer moving parts meant fewer failures. Lower engine height improved packaging. Smaller dimensions reduced weight compared to overhead cam competitors. Servicing remained straightforward. A competent mechanic could replace lifters or camshafts without removing the engine. Valve adjustments weren't even necessary thanks to hydraulic lifters. Most importantly, it worked. Fleet mechanics quickly noticed something unusual. These engines just wouldn't quit. Stories began circulating across North America. Silverados crossing 300,000 miles without internal repairs. Utility trucks idling 8 hours every day for years. Delivery vans running constantly in stop-and-go traffic. Municipal vehicles subjected to the kind of abuse that normally destroys drivetrains within months. Oil changes skipped, maintenance ignored, coolant neglected until it turned brown. Still running. One fleet supervisor reportedly joked, "The truck rusts away before the engine notices." That wasn't far from reality. Independent contractors started sharing their own experiences. Landscape companies running trucks past 400,000 miles. Excavation contractors whose Silverados outlasted the businesses themselves. Welding trucks that spent entire careers idling at job sites. Tow truck operators who finally sold their rigs after the transmissions failed for the 3rd time while the original engine kept running perfectly. These weren't isolated incidents. They became normal, expected. The 6.0 Vortec earned a reputation for being genuinely unkillable. And then something unexpected happened. Performance enthusiasts discovered the 6.0 Vortec. Its iron block made it heavier than aluminum LS engines, but it was also dramatically stronger. Turbochargers, superchargers, nitrous oxide. The 6.0 accepted all of it. Builders routinely pushed stock bottom-end LQ4 engines beyond 600 horsepower with forced induction. Some crossed 800 horsepower using careful tuning. Others exceeded 1,000 horsepower after upgrading pistons and connecting rods. The factory rotating assembly could handle boost levels that would grenade most engines. Suddenly, junkyard truck engines became racing legends. A complete used LQ4 often cost less than rebuilding older big block V8s, sometimes significantly less. Salvage yards were full of wrecked Silverados with perfectly good engines, trucks that had been rear-ended or T-boned, vehicles totaled by hail damage or flood. The engines themselves remained flawless. Enthusiasts could buy a complete running engine for under $1,000. That combination of affordability and strength transformed grassroots drag racing. Quarter-mile builds producing 10-second passes became surprisingly common. Some dedicated race cars eventually dipped into the 9-second range while still retaining factory blocks. Street-driven vehicles with full interiors and air conditioning ran 11-second quarter miles on pump gas. Off-road trucks used forced induction 6.0 engines to conquer desert races. Rock crawlers appreciated the low-end torque and mechanical simplicity. Mud racers pushed them to absurd power levels. Most people don't realize just how incredible that was, because those engines originally spent their lives hauling construction equipment, not racing. They were designed for durability, not performance. Yet they excelled at both. But despite all that success, there was a problem. Actually, several problems. The first was fuel economy. The 6.0 Vortec wasn't terrible for its era. Trucks equipped with these engines typically achieved somewhere between 12 and 16 miles per gallon in mixed driving. That seemed acceptable in the early 2000s, but times had changed. Gasoline prices climbed. What cost $1.50 per gallon in 2000 approached $4 by 2008. Suddenly, filling a 30-gallon truck tank became painful. Corporate average fuel economy regulations became increasingly strict. CAFE standards were originally designed for passenger cars, but light trucks faced growing scrutiny. Manufacturers needed fleet-wide averages to meet specific targets. Every vehicle mattered. Every tenth of a mile per gallon counted. Customers demanded more miles per gallon without sacrificing towing capability. They wanted the same payload ratings, the same trailer weights, the same durability, just with better efficiency. Physics, however, refused to cooperate. Large displacement, naturally aspirated V8s consume fuel, especially inside heavy pickup trucks. Aerodynamics could only improve so much. Weight reduction had limits in work trucks. Gearing changes helped slightly, but affected performance. The engine itself needed fundamental changes. Then emissions regulations tightened again. Meeting new standards required increasingly complex calibration strategies. Catalytic converters improved. Engine management became more sophisticated. Oxygen sensors multiplied. But every year the compliance window became narrower. Hydrocarbon limits dropped. Nitrogen oxide standards became stricter. Particulate matter faced new restrictions. GM engineers faced an uncomfortable truth. The 6.0 still had room for improvement, but not enough, at least not without fundamentally changing the engine. Port fuel injection had reached its efficiency limits. Static valve timing couldn't optimize across the entire RPM range. Fixed displacement meant no ability to reduce cylinder count during light loads. Compression ratios were constrained by pump gasoline octane ratings and the limitations of port injection. Then another challenge appeared: competition. Ford introduced increasingly powerful versions of its modular V8 before transitioning toward larger displacement Boss-based engines and eventually turbocharged EcoBoost technology. The EcoBoost V6 changed everything. Suddenly, customers could get V8 power with better fuel economy. Towing numbers remained competitive. Acceleration actually improved in some cases. Ram continued refining its Hemi lineup. The 5.7-liter Hemi offered more horsepower. The name alone carried marketing weight. Variable valve timing and cylinder deactivation improved efficiency. Customers expected more horsepower every few years, more torque, more efficiency, more refinement, quieter operation, smoother idle, better throttle response. Doing all four simultaneously became nearly impossible with the aging 6.0 architecture, so GM started developing something new. The result became the Gen V small block. At first glance, it looked similar. Pushrods remained, 2 valves per cylinder remained, camshaft in block. But internally, everything evolved. Direct fuel injection dramatically improved combustion efficiency. Fuel sprayed directly into the cylinders at high pressure. Timing could be optimized for every engine speed and load condition. Combustion temperatures dropped, efficiency increased, power improved. Continuously variable valve timing broadened torque curves. The camshaft could advance or retard based on driving conditions. Low-end torque improved without sacrificing high RPM power. Emissions became cleaner across the entire operating range. Cylinder deactivation became far more sophisticated. Active fuel management allowed the engine to run on 4 cylinders during light loads. The transitions became nearly imperceptible. Fuel economy improved significantly during highway cruising. New combustion chambers increased thermal efficiency. Higher compression ratios became possible without detonation. The entire package represented years of development, millions of dollars in research, countless hours of testing. The replacement wasn't simply another V8. It represented an entirely different philosophy. One engine symbolized absolute durability. The other chased maximum efficiency while preserving respectable reliability. And that transition divided truck enthusiasts almost immediately. The 6.0 eventually gave way to engines like the 6.2-liter L86, and for heavy-duty trucks, the all-new 6.6-liter L8T. On paper, these newer engines surpassed the old workhorse. The 6.2 generated around 420 horsepower and 460 pound-feet of torque. Fuel economy improved by 2 or 3 miles per gallon in most driving conditions. Throttle response sharpened. Acceleration became noticeably quicker. Emissions dropped substantially. Later, the 6.6-liter L8T delivered roughly 401 horsepower and an impressive 464 pound-feet while retaining the robust iron block philosophy heavy-duty customers expected. GM had learned from feedback. Commercial customers didn't want complicated efficiency features. They wanted reliability above everything else. But many longtime owners remained skeptical. Why? Because reliability isn't measured on a specification sheet, it's measured over decades, and the 6.0 had already proven itself. Mechanics knew exactly how to repair it. Every repair shop had experience. Diagnostic procedures were well established. Parts were inexpensive. Aftermarket support was enormous. The engine rarely surprised anyone. Even common issues tended to be relatively minor. Exhaust manifold bolts occasionally snapped. The bolts would corrode and break from heat cycling. Replacement required a few hours of labor. Annoying, but not catastrophic. NOx sensors sometimes failed after moisture intrusion. They were mounted in the valley under the intake manifold. Coolant or water could compromise the sensors. The fix cost a few $100s. Oil consumption appeared on certain high-mileage examples. Piston rings would wear. Valve seals would harden. The engine might consume a quart every 1,000 miles. Owners just added oil and kept driving. Coil packs eventually wore out. Individual cylinders would misfire. Replacing the failed coil took minutes. Water pumps failed after years of service. Bearings would wear. Seals would leak. Replacement was straightforward and inexpensive. None of those problems terrified owners. They simply fixed them and kept driving. Contrast that with newer engines packed with direct injection systems, variable valve timing actuators, active fuel management components, and increasingly complex electronics. Performance improved, complexity exploded, and complexity almost always introduces new failure points. Direct injection caused carbon buildup on intake valves. Cylinder deactivation wore valve springs unevenly. Variable valve timing actuators failed and threw check engine lights. High-pressure fuel pumps wore out prematurely. Repairs became expensive. Diagnosis became complicated. Ironically, GM itself recognized part of this. When engineers designed the 6.6-liter L8T for heavy-duty trucks, they intentionally omitted active fuel management. No cylinder deactivation, no start-stop system. They prioritized durability over squeezing every possible fraction of fuel economy. It was almost as if they had quietly acknowledged what truck buyers valued most all along: dependability. You can probably guess what happened next. The used market exploded. Contractors actively searched for older 2500 HD Silverados equipped with LQ4, LY6, or L96 engines. Prices climbed. Some trucks with over 250,000 miles still sold for astonishing amounts simply because buyers trusted the drivetrain. Clean examples became surprisingly valuable. Well-maintained work trucks commanded premiums. Meanwhile, engine swap culture embraced the 6.0 even more enthusiastically. Classic Chevelles, square-body pickups, C10S, Fox-body Mustangs, Jeeps, drift cars, off-road racers. Even import builds occasionally featured them. The 6.0 Vortec found new life everywhere, not because it produced the highest horsepower, because it represented unmatched value. Strong block, reliable oiling, excellent aftermarket support, affordable replacement parts, proven track record. Tuners discovered another advantage. The LS-based architecture responded beautifully to modifications. A camshaft upgrade alone often unlock substantial gains. Swapping to a more aggressive profile could add 50 horsepower. Cylinder head improvements added even more. Ported heads improved airflow dramatically. Valve spring upgrades allowed higher RPM operation. Long tube headers, proper tuning, and intake modifications routinely pushed naturally aspirated builds beyond 450 horsepower, all while maintaining excellent street manners. Forced induction opened another world entirely. Builders often joked that the engine didn't ask whether it would survive boost, it asked how much. That's a reputation engineers dream about creating. So, did Chevrolet really kill the 6.0 because it failed? Absolutely not. The real reason was that the automotive industry changed around it. Fuel economy standards tightened, emissions regulations became stricter, customers demanded more refinement, more technology, quieter cabins, faster acceleration, and lower operating costs simultaneously. Meeting all those demands required engines designed for a different era. The 6.0 simply belonged to another philosophy, one where simplicity beat sophistication, where cast iron outweighed lightweight alloys, where mechanical strength mattered more than computer-controlled efficiency, where an engine was expected to run forever rather than just meet warranty requirements. And despite disappearing from new Silverado production, its influence never truly ended. Many engineering principles carried into later small block designs. The basic architecture remains recognizable. Its reputation continues growing every year. Thousands remain hard at work across North America. Some have crossed 400,000 miles. Others have surpassed 500,000 with proper maintenance. A few have reportedly exceeded 600,000 miles. They're still hauling trailers, still towing equipment, still powering work trucks, still starting every morning. Not many engines can claim that. That's why mechanics still recommend them. That's why enthusiasts still hunt for them. That's why salvage yard prices keep rising. And that's why the 6.0 Vortec has become one of the most respected truck engines Chevrolet ever built. In the end, Chevrolet didn't eliminate the 6.0 because it was weak. They didn't discontinue it because customers were unsatisfied. They didn't kill it because it couldn't do the job. They retired it because the world demanded something different. Regulations changed, expectations evolved, technology advanced. But durability has a funny way of creating legends. Horsepower records get broken, fuel economy numbers improve, technology keeps evolving, yet decades later, people still search for one specific engine because they trust it with their livelihood. That's a legacy very few power plants ever earn. If you enjoyed this deep dive into one of Chevrolet's greatest truck engines, let me know in the comments which legendary V8 you want to see next. And if you love the hidden engineering stories behind America's most iconic engines, make sure to subscribe so you don't miss the next chapter.